Hello students, thought I'd give this a shot. We're getting ready for the coronavirus, so might as well see if my materials are working. Okay, I'd like to talk to you today about redox reactions. Reduction oxidation reactions. So as it happens, we follow the path of electrons through reactions. You'd know that an ionic reaction involves a metal and a non-metal, and that's a complete transfer of electrons. A covalent bond involves a sharing of electrons. We don't so much bother with the metallic bonds here. Reduction oxidation reactions are reactions where we track the progress of electrons through the reaction itself. So we've got two words here, which is reduction and oxidation. Reduction and oxidation. Which are forming the parts of the words redox. Now I use a, I don't know what you call these things, acronym? Oil rig. Oxidation is loss, reduction is gain. Now what we're talking about there is oxidation is loss of electrons and reduction is gain of electrons. So I've got a pointing stick now. So when we say something's oxidized, the chemical species has lost electrons, and when it has reduced, it's gained electrons. Now this might sound a bit funny to you. How can something be called reduction if it's gaining something? How can it reduce when it gains something? Well, this is a historic term. So back in the day when people used to heat up old ores to get the metal out, they would find that once the metal had come out, that the mass of the ore had reduced, which makes sense because you strip the metal out of the ore and its mass is reduced. So that's where the term reduction comes from. It's from the reduction of the metal itself. So yes, that's going to add some definitions here. So reduction is a reaction where a chemical gains electrons, which I'll indicate with E minus, and oxidation is a reaction where I should say chemical species. A chemical species so reduction, a reaction where a chemical species gains electrons, and oxidation, a reaction where a chemical species loses electrons. Now these are often referred to as half equations, because if you want to gain an electron, then someone else is going to have to lose it. So in an oxidation reduction situation where a reduction has taken place, an oxidation must also take place. This reaction cannot proceed unless the one which is going to receive the electrons is able to get them from the one that's going to lose them. So what you find then is the electrons are now participating in the chemical reaction equation itself. So a reaction where a chemical gains electrons. An example of that would be, what can we do? Cl. So let's do Cl2 plus 2E minus, plenty short, makes 2Cl minus. So you can see now that when we go chlorine, a diatomic chlorine molecule, and then you force 2 electrons on it, will make 2 chloride ions. Now in this situation here, the chlorine's been forced to take on the electrons. So it's been reduced because it has gained electrons, and when the electrons are being gained by something, then they're on the left-hand side of the equation, so they're with the reagents, not with the products. Whereas if it's oxidation, let's say we had Fe2 plus, and it's going to become the 3 plus ion, then it's going to make Fe3 plus E minus. So now you can see that the electrons for the oxidation reaction are on the right-hand side of the products. So you can tell if it's reduction because they're on the left, and it's oxidation if they're on the right, because this one has lost it and this one has gained it. Right, I need to get a photo of the board. And then we're going to rub this out. Now, the next step in this is to be able to assign what we call an oxidation state to elements. Now, even though in covalent bonding the element is sharing the electrons, when we assign an oxidation state, we actually sort of consider that it's being transferred. So, there's a set of rules that are involved in assigning an oxidation state to an element. It indicates if the element's gone negative or positive. So we've got to follow these rules in order to achieve the oxidation state. And now I'm going to pull them out. I'll probably just speed this stuff up when I'm doing this. So rule number 1, the oxidation number of a free element is 0. So 1, free, it's an R, element, the oxidation number is 0, meaning it hasn't lost or gained any electrons. An example could be helium, the noble gas. Another example could be solid aluminium in a metallic bond. Things that sit alone. A molecule of mercury, alone, uncharged, it has an oxidation state of 0, which indicates that it has not lost or gained any electrons. Okay, 2. Now we're going to write OX and then a hash, which will mean oxidation number of a monoatomic ion is its charge. So an example would be, so the oxidation number of a monoatomic ion is equal to its charge, Na plus, that has an oxidation number of +1. Cl minus has an oxidation number of -1. Al3 plus, aluminium 3 plus ion, has an oxidation number of +3. O2 minus, the oxide ion, has an oxidation number of 2 minus. So whatever the charge is on the monoatomic ion will equal its oxidation number, whether it's negative or positive. And you notice that as you're losing electrons it goes positive, and as you're gaining electrons it goes negative. Okay, the next rule, 3. The usual oxidation number of hydrogen, oxidation number of hydrogen in a compound is always +1, except there's one example where it's not, which is metal hydrides. So metal hydrides, in that case it's going to be -1. So if we look here at an example of water, H2O, then the oxidation number of hydrogen in this will be +1, because it's only got 1 electron to give away, so it's going to be +1 every time. How about, what's another one? CH4, methane. In each of these cases, it's still going to be +1, because it only has 1 electron to give away. Now, oxygen and carbon, yeah, you know, they don't have a problem sort of taking on electrons, but then if you look at something like NaH, sodium hydride, sodium is so damn not electronegative that it's able to force its electron onto hydrogen. So this is an example of one of the exceptions, which is a metal hydride. So the sodium is forcing its electron onto the hydrogen, and consequently the hydrogen receives a -1. So if it's a metal hydride, that's where you're assigning it a -1. Otherwise, in all other compounds, hydrogen is always +1. Next step, 3, 4. oxidation number of oxygen is -2. Always. Unless, again, we've got another exception, unless, sounds like I'm saying something out of the redox, unless it's in hydrogen peroxide, H2O2. So, if you look here, oxygen in water, and this water will be -2. If we did, what's another one? Oxygen in SO2, sulfur dioxide. Again, here, it's going to be -2, obeying the rule. But if you've got something like H2O2, well, if we were to do up the Lewis dot diagram, oxygen's got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Yeah, I don't know where I got the 7 from. We do another one. 1, 2, 3, 4, 5, 6. And you've got 2 hydrogens, which has got a 1, and another hydrogen, which has got a 1. So we can join a hydrogen between those two, and we can join a hydrogen between those two. And then you've got now just 2 electrons that we need to pair on the oxygens there. So you've got a bond there, and it creates this molecule H bond O bond O bond H, which is your H2O2. This is a really unstable molecule. Of course, hydrogen only ever has 1 electron to give. And in the case of this kind of molecule here, the oxygen hasn't received 2 electrons. See, this oxygen here has only received 1, and so has that. So consequently, in this situation, the oxygen has a oxidation number of -1, because it's just both of them have gained only 1 electron from hydrogen. So these 2 rules here, 3 and 4, both have exceptions. Oxidation number of hydrogens always +1, unless it's in a metal hydride. Oxidation number of oxygen is always -2, unless it's in hydrogen peroxide. Okay, the total oxidation numbers in a covalent compound must add up to 0. So 5 covalent, that's an O there, covalent compound must be 0. Alright, let's pull out a covalent compound. Water, H2O. Oxygen is -2 based on that rule there. Hydrogen is +1 based on that one. And you've got 2 hydrogens here. So you've got +1, +1. 2 +1s balances out a -2. Overall, completely balanced. How about, let's do another one. Covalent compound. Carbon dioxide, CO2. Each oxygen is going to be -2, -2. So that's a -2 and a -2 there. Overall, that's going to become -4, which means that the carbon must be +4. So +4 balances out -4 and it comes to 0. That's how we know carbon's a +4 compound. Let's do SO2 again. SO2, oxygen, -2, -2, because there's 2 lots of oxygens there. That means that that sulfur's in at +4. And so that's an example of where the compounds must balance out to equal 0. And then if we got a polyatomic ion, 6 polyatomic ion, the oxidation number must be equal to the charge. Alright, I'll pull out a few polyatomic ions here. Let's try, I think green would probably be good here. Phosphate, PO4, and that's 3-. So each oxygen is going to be -2, and we've got 4 of them, which is going to make us -8, which must mean that the phosphorus will have to balance it. But the thing is, instead of going to 0, because the polyatomic ion's oxidation number must be equal to its charge, well, phosphate has a charge of 3-. So how do you go from -8 to -3? well, that's a +5. So the phosphorus in this case is going to have a +5 oxidation number. Because 5 and then 6, 7, 8. So that's how we know what the oxidation number of phosphorus is. What that tells us is phosphorus has given away 5 electrons to the 4 oxygens there in this polyatomic ion. What's another one? Cr2O7, dichromate. 7 oxygens is going to be -14. 7 times -2 is 14. And that's a 2- ion. So the chromiums, we want to go from -14 to -2, which means we need to add 12. So it's going to be +12 from those chromiums, but there's 2 chromiums in there, so each chromium is in a +6 oxidation state. Add 2 +6s, that makes +12, balances out the -14 with a 2- overall. So that's how you apply oxidation numbers. You should have a look in your textbook now and have a crack.